for graphs on endo and exothermic reactions. We're graphing these energy diagrams, which is one of the last tasks we need to accomplish in order to take that summative. All right. So if you guys all open up your Canvas pages and you go to the energy diagram practice, we're going to be going through that together. So if you guys open that up, it should look like this when you open it up. Endo and exothermic graphing. So there's 4 example problems or 4 practice problems that we have. So when we're doing this, it says we need to draw the graph of energy versus time for the following reactions, making sure that we include title and label all the parts, including products, reactants, activation energy, and delta H. So that's a lot of information we have to put on these graphs. So it says everything we need to do. The first thing to do before anything else can happen is we need to identify endothermic or exothermic. So if we look at this equation, we have to figure out if it's an endothermic reaction or if it's an exothermic reaction. So do you guys remember what an endothermic or exothermic reaction are? Do you guys remember what those were?
Cold and hot? I don't know.
What is endothermic reaction or an exothermic reaction? Remember?
Exo is cold and endo is hot.
Okay, so I like that if we remember it that way, except for it's going to be a little bit challenging when we think about systems versus surroundings. We should remember that endothermic, if we write it up here, endothermic absorbs or gains energy. So it is getting hot. The system gets hot, which means everything around it gets colder. So endothermic, it absorbs energy or absorbs the heat. So everything else is going to get cold around it. And then exothermic releases heat or energy. All right. So if we look at this reaction, do you guys remember what the 2 sides of this yield sign stand for? Do you guys remember what those 2 sides are? We have our yield sign. What are the other 2 sides?
Addition sign.
So this side is what? What'd you say?
The addition sign.
The addition side. So we have our addition sign in there, but do you remember what that whole side of the reaction is called? Those 3 things, or the things on the left side of that yield sign. What side is this called? We have
reactants.
Exactly. We have our reactants over here. And that means on the other side, the right side of that yield sign, what are those things called?
Products.
Products. Perfect. So we have our reactants and we have our products. And our reactants are this A, this B, and this 200 kilojoules, which is just our unit for energy or unit for heat. Just so you know, kilojoules is unit of energy. And then we have our products, which is just the C. So based on just this reaction, just this title or this reaction, do we think that this is an endothermic reaction or exothermic? And tell me why.
Endo?
Endothermic. And why are you saying endothermic?
it looks like it's adding more to one place.
Exactly. We are adding energy here. This energy right here is being added to the reactants to make this product, which means that we are going to have more energy in our products than we did in our reactants because we needed to add that energy to make this product. So we're adding energy or making an endothermic reaction. So this is endothermic. So that's going to be super important when we actually draw this graph. So when we're drawing these graphs, the first thing we have to do is we have to draw an X and a Y axis. So if I draw my X and Y axis, you can start at the very edge. You can start a little bit above the edge. It does not matter. We are always going to start on this X, on the Y axis. We're always going to start somewhere on that point. It says in our directions way up here, it says that we need to draw the energy versus time graph. We need to make sure we label the titles and the X and Y axis. So what is our title of our graph going to be? Or what do we think the X and Y axes are? Any ideas?
Energy and time.
Energy and time are going to be our X and Y axes. Over here is going to be our energy. And this is going to be our time. Our title, we can do a couple of things. We can just label it our energy versus time graph. We can label it energy versus time. We can label it formation of C because we're making C. Whatever you want to label that title, just tell me what you are doing, what you are looking at. It's an energy versus time graph, so we can label it energy versus time. Formation of C. If we knew what our product was, this is what we're making in the end. So that's the formation of this product. Something that gives me a description of the graph. So we've labeled our title and our X and Y axes. Now we actually have to draw this graph. And so yesterday you should have seen some graphs of energy being added or released in 4 different salts in a hot pack versus a cold pack when you get injured on a sport. So when we draw these graphs, if you remember from way back when, we have to draw something called activation energy. And we have to be able to draw this as part of our reaction. The other thing we have to be able to draw is our reactants and our products side. And we need to know if our reactants or our products is going to be larger or higher up. We're not going to start at 0. Because we always have some amount of energy in these reactants. In those 2 compounds or 1 compound, there's always a little bit of energy or a lot of energy. So we have to put these lines for our reactants and our products, and we have 2 options. We can have our reactants start here and our products be up here. So this is option 1. Or we can have option 2. Our reactants start up high and then our products are down at the bottom. So do you think we're going to gain energy like this or gain energy like this?
One.
Option 1, perfect. We are gaining or absorbing energy. So our products are going to have more energy than those reactants. So it's going to be more like reaction number 1. So we're going to start with our reactants way down here. And we're actually going to label those reactants on this line. So our reactants are A and B for this problem. So we're going to put A plus B right here. If there was a 2 in front of one of them, we'd put the 2. Anything on that left side of our yield sign that's not a energy value goes on this reactants line. Our product is up here. So our product is somewhere up here. And we're going to put our product on this line. So we're going to put C on that line. Now, yesterday, those graphs weren't 100% accurate because it showed a line going straight from A plus B. It showed a line going up to C. And that's not going to be perfect because that doesn't show that we put in energy to make this reaction happen. All reactions require this thing called activation energy. So I'm going to write right here, activation energy. Does anybody have a guess as to what activation energy would mean?
A little boost.
I like that. A little boost. It's that energy that's going to be required to make this reaction happen. Normally, reactions don't just happen randomly. Something else has to be added into it. If we think about that hot and cold pack, we have to squeeze the water, the bag that's full of water, to make the water react with the hot cold pack. And then you shake it to make sure that the ions are being dispersed between the water. So there has to be energy added to make this reaction happen. So some amount of energy has to be put in order for this reaction to happen. So we have to go a little bit higher than our products. We have to go up a little bit more, and then we come back down. So this area right here is going to be our activation energy. Is right here. So we can separate this with this section right here. What do we think that section is going to be then? If that little section from that's past our products is our activation energy, the rest of that must be the energy that we either absorbed or released. So it's that delta H, that change in energy between our products and our reactants, the energy we absorbed or released. So is this energy absorbed or is this the energy released here?
Absorbed.
It's absorbed because we're gaining energy to get to our products. So we had to put more energy in, which means that our delta H, which is this green value up here, that 200, is that 200 kilojoules? Is that going to be a positive or negative?
Positive.
It's a positive 200 kilojoules because we are gaining that energy. You do have to label activation energy each time you draw these graphs. So if you want to label it with a shorthand, this is an option. You don't have to use it, but capital E with a little a as a subscript tells me that you're talking about the activation energy. So if you wanted to shorthand write it, it's EA for activation energy. Are there any questions on how to draw this graph? All right, you have example number 2, and I want you guys to try this one on your own. I'll give you guys like 4 or 5 minutes actually to try this problem on your own, to try graphing all of it, adding in the labels, adding in the reactants and the products, determining all that information. But I do want to go over together, is this an endothermic or exothermic reaction? What do we think? Anybody have an idea, a guess?
Endo.
All right, you said endothermic reaction. In an endothermic reaction, do we absorb energy or do we release energy?
We get
We
so
get
absorb.
we absorb that energy. Perfect. So in this, our reactants is what we have to start with. Our products is what we make at the end. So if we're making this energy right here, this energy gets made. That means is it a reactant or is it a product?
Product.
It's a product. So it's made at the end, or if it's made at the very end, that means we are releasing this energy. So if it's made at the end, if it's a product, it's being released. So does that change our answer about endothermic versus exothermic?
Yes.
So what is it?
Exo.
Exothermic, perfect. So if it's at the product side, it's going to be an exothermic reaction. If it's at the reactant side, it's a endothermic reaction. All right. Take the next 4 minutes to try and graph this one, and then we'll go through it together. All right, ladies and gentlemen, can anybody tell me a step that they took to try and graph this problem? Example 2. What's the first thing I should do?
Label your X and Y.
Label your X and Y. So you're making our X and Y axes. We're going to label those axes. And what's my label for my X axis?
And time.
Time, perfect. And what's my label for my Y axis?
Energy.
Energy, perfect. All right. Well, anything else I need to label before I get started?
The title.
The title. What do we label our title?
Energy versus time.
Perfect. All right. So now we've labeled all the titles and their axes. So now we have to draw our graph. When we draw our graph, do we want our reactants or our products to be higher?
Reactants.
Our reactants are going to be higher than our products. So our reactants will be higher than the products because it's an exothermic reaction. All right. So on my reactants line, do I have to put anything? Am I done?
Label your reactants at the
Label my
top.
reactants. So I'm going to put my H2 plus my I2. All right. On my products line, do I have to label anything?
Your products.
My products, so I'm going to put the 2HI down here. And then do I just draw a line like this, going from here to here?
No.
No. What else do I have to include on that line?
Activation energy.
The activation energy. And that's always the energy required to make this reaction happen, which means that we have to start up here and we're going up first and then down. So we have an activation energy right here. So we'll label it EA for activation energy. And then we have the rest of our energy that goes here. And that's our delta H. And what does our delta H equal on this one?
$200.
200 kilojoules. All right. And so it's an exothermic reaction. So does that change the sign? Do we have a positive or negative 200 kilojoules?
Negative.
This one's going to be negative because it's exothermic, or we've lost or released that energy. So when we go down, our delta H is always negative here because we've released that energy at the end. Any questions on graphing endothermic and exothermic reactions? All right, guys, then you have two more practice problems, practice problem 1 and practice problem 2. Go ahead and do those two problems. You do not have to stay to complete those two problems. So if you're leaving, have a good rest of your day. If you're staying and if you have questions,